Next, we're going to start looking at continuous random variables and their distributions. Now, recall that a continuous random variable is one that can take on any value in one or more intervals on the real line. Now, when we talked about discrete random variables, there was associated with that random variable what was called a PMF, or probability mass function. And that PMF gave us the probabilities associated with each of the values in the sample space of the random variable. When we're dealing with continuous random variables, we don't have a PMF. What we have is what's called a probability density function, or PDF. Now, let x be a continuous random variable. Suppose there exists a function f that satisfies the following three conditions. The first condition is that the function always evaluates to a non-negative number. Regardless of the value at which we evaluate it, when we plug it in, we always get something that is non-negative. The PDF never satisfies or never evaluates to a negative number. It's always greater than or equal to 0. The second condition that the function f must satisfy is that when integrated over the entire real line, it integrates to 1. And then finally, for all real numbers a and b, where a is less than or equal to b, the probability that the random variable takes on a value between a and b is given by the integral of f over the interval from a to b. So when such a function exists, it's called a probability density function, or PDF, of the random variable x. And in some cases, we'll describe it as the PDF of the distribution of x. Now, whereas when we were dealing with discrete random variables, the PMF gave us the probabilities associated with the random variable, PDFs are somewhat different because of the nature of continuous random variables. PDFs don't give us the probabilities that x takes on particular values. It gives us probability densities associated with x taking on a particular value. Probabilities involving x correspond to areas under the graph of the PDF of x, which is again given by the integral of this PDF over the appropriate interval. So when we're talking about probabilities of continuous random variables, we're talking about the probability that the random variable takes on a value over some interval, not particular values. Now, when we were dealing with discrete random variables, there was associated with the distribution a function called the CDF, the cumulative distribution function. And we have the same kind of function when dealing with continuous random variables, the cumulative distribution function. Remember that the cumulative distribution function is a probability accumulator. And so we have the same kind of idea and the same kind of function when we're dealing with continuous random variables, because we can, in fact, accumulate probability associated with continuous random variables. So let x be a continuous random variable now with sample space script a and PDF lowercase f. And for each real number x, the CDF is defined by this expression here. So again, we're going to denote the CDF using an uppercase version of the same letter that we're using to denote the PDF. So we're using lowercase f to denote the PDF in this notation. And so we would use uppercase f to represent the CDF, or cumulative distribution function. And so at this real number x, which is the value at which we're going to evaluate the CDF, what this is defined to be is the probability that the random variable, the continuous random variable x, is or takes on a value less than or equal to the specified value little x. So this is the same exact definition, conceptual definition, that we had when we were dealing with discrete random variables, but now we're dealing with a continuous random variable. And because we're dealing with a continuous random variable rather than a discrete random variable, instead of summing a PMF to get these probabilities, we're going to integrate the PDF from minus infinity up to the value specified as the argument of the CDF, which is x. And so you can see here that lowercase x shows up as the upper endpoint of the integral we're using to calculate this probability. Remember that from the previous slide, in looking at these three conditions that a function must satisfy to be a PDF, that for probabilities like this, we obtain these probabilities by integrating the PDF over the appropriate interval. And it's acceptable to have minus infinity as the lower endpoint, and so we would have minus infinity as the lower endpoint of the interval, and that's what we're doing here. Now let's talk about the relationship between the CDF and the PDF. And so let x be a continuous random variable with PDF lowercase f and CDF uppercase f. Then the PDF and the CDF are related in the following ways. As we saw on the previous slide, the CDF is obtained from the PDF by integration. In particular, by integrating the PDF from minus infinity up to the argument or the value specified as the argument of the CDF. In addition, the PDF can be obtained from the CDF by differentiation. So if we have a formula or expression, a differentiable function for the CDF, then we can differentiate, take the derivative of that CDF, and that will give us the PDF. So let's look at an example of this. This is example 32. And so let's let x be a continuous random variable with PDF of the following form. So the PDF of x, evaluated at x, is the expression for the PDF is equal to c times x, as long as x is greater than 0 and strictly less than 1. And if x is any other value, if x is less than or equal to 0 or greater than or equal to 1, then the PDF evaluates to 0. And so what we want to do is to, several things. We want to first find c, because we haven't indicated what c is here, but we want to find the numerical value of c that would make this a PDF. Then we want to, from that fully specified expression for the PDF, we want to derive the CDF of x, and then we want to compute several probabilities. We're going to compute the probability that the continuous random variable x is less than or equal to 1/2. We'll compute the probability that the continuous random variable x is strictly greater than 3/4, and then we'll compute the probability that the random variable x is greater than 1/2 and less than or equal to 3/4. Now let's first find c. We need to find c before we can do anything else. Now recall that in order for f to be a PDF, when integrated over the entire real line, it must integrate to 1. And so we're going to use that constraint. We're going to use that required condition in order to help us find what c must be equal to. And so we know based on that condition, based on that constraint, that 1 is equal to the integral of this PDF from minus infinity up to infinity. Now I'm going to decompose the integral, and in particular decompose the real line, which is the interval over which we're evaluating this integral. I'm going to decompose the real line into 3 subintervals, from minus infinity up to 0, from 0 to 1, and then from 1 to positive infinity. And the reason I'm going to do that is because the expression for the PDF differs over those 3 intervals. And so I need to decompose that real line, that interval over which we're integrating, in order to make sure that I get the expression, the expressions put in here correctly. So over the interval from minus infinity to 0, the PDF evaluates to 0. In addition, from over the interval from 1 to positive infinity, again, the PDF evaluates to 0. So I can plug those values in there. Over the interval from 0 to 1, the PDF evaluates to c times x. Okay, and so you can see here why I needed to decompose the real line from minus infinity up to positive infinity into 3 subintervals. And then So this and by the way, this decomposition, I'm using a property of integration which allows me to decompose this integral in this way right here. Now, when we integrate the 0 function over any interval, that integral is going to be equal to 0. And so the first integral here is 0, and the last integral, the third integral, is 0. All right, and then what we have left is the integral from 0 to 1 of c times x. All right, so we've got that simplified there. So we know that 1 is equal to the integral from 0 to 1 of c times x. Now, I can pull the constant c out of the integral. And so what we're left with then is c times the integral from 0 to 1 of x dx. Now, by the fundamental theorem of calculus, this integral is equal to this expression here, which the way we evaluate this is we plug in 1 for x, and so we would have 1 squared, or 1 over 2. And then from that we subtract this expression where we plugged in 0. All right, and then so we have 1 half minus 0 halves, or 1 half minus 0. Now notice that I pulled the 1 half out of that expression, so I've got this out here in front, c over 2, and so that leaves this as being 1 squared minus 0 squared, or 1. And so the integral that we're looking for, all right, so we see here that 1 is equal to c over 2. And so this implies that c must be 2. Now let me just, for those of you who are maybe a little bit rusty on the calculus and rusty on the fundamental theorem of calculus, let me just say that we're going to be using the fundamental theorem of calculus in this class quite a bit. All right, and so here's the justification for going from this step to this step. The antiderivative of x, right? The antiderivative of the integrand here is x squared over 2. Now the antiderivative, or by antiderivative, what we mean is the function that which, when differentiated, gives us the integrand. So when we differentiate x squared over 2, we get x. The fundamental theorem of calculus says that if we can identify the antiderivative of an integrand like this, right, in a definite integral, then the way that we calculate this integral is to evaluate the antiderivative at the upper end point, evaluate the antiderivative at the lower end point, and then take the difference. And so that's what we're doing right here. All right, and so that's how we got 1 half. So the bottom line then is that in order for 1 to be equal to c over 2, it must be that c is equal to 2. All right, and so now we can plug that into the expression for the PDF that we had in the statement of the problem, and we get the fully specified expression for the PDF. For values of x between 0 and 1, the PDF evaluates to 2 times x. And then for any other value of x, the PDF evaluates to 0. Now let's just point out a few things about this PMF. Based on the way that we've defined it here, and in particular by including this piece right here, the PDF, this function is now defined at every x on the real line. Notice also that the sample space of x is the set of values over which the PDF is strictly positive. The PDF is strictly positive at every point in the sample space of x. And then finally, the PDF is 0 at any point not in the sample space of x. Now let's find the CDF. And I've got a little typo here. Oh, no, this is fine. We're going to denote the CDF by cap f. That's fine. All right, so we were using, let me just go back here. We're using lowercase f, all right, to denote the PDF. And so we're going to, by convention, use the uppercase version of that letter to denote the CDF. And so we're going to denote the CDF by cap f. Now, the sample space of x, as discussed on the previous slide, is the open interval from 0 to 1. All right, and if we remember that the CDF is a probability accumulator, then we know that if we evaluate the CDF at any value of x that is less than or equal to 0, then we have not accumulated any probability up to that point. And so because of that, the CDF is going to be 0. The accumulated probability is going to be 0 when evaluated at any value of x less than or equal to 0. Okay, and then if we evaluate the CDF at any value of x greater than or equal to 1, well, we know at that point, at any such x, we know that we have accumulated all the possible all the probability that there is to accumulate. And so the CDF must accumulate to 1 at any value of x that is greater than or equal to 1. So we know those two things without really having to do any calculations at all, just thinking about the definition of the CDF and that it is a probability accumulator. Now, to determine the expression for the CDF for values of x that are between 0 and 1, we need to do some calculations, some derivation. So at such a value of x, the CDF evaluated at x is going to be equal to, is defined to be, the integral from minus infinity up to x, the argument of the CDF, of the PDF. Now notice that we can't use the same letter. Typically we would use x as the argument or the variable of integration here, but we can't do that because x is already being used as the upper limit of integration. So we've got to use some other variable, and we'll just use t. So remember that the CDF evaluated at little x, by definition, is the probability that the random variable x is less than or equal to little x, and so that's given by this integral here. Now again, I'm going to do this thing where I decompose the interval over which I'm integrating to those intervals where the PDF has different expressions or values. And so I'm going to decompose the interval from minus infinity up to x into two intervals, from minus infinity up to 0, and then from 0 up to x. And then using properties of integration, this integral is equal to the sum of these two integrals. Now again, over the interval from minus infinity to 0, the PDF is 0, so we plug that in. And then over the interval from 0 to x, because x is between 0 and 1, we know that over that interval, the PDF evaluates to, in this case, 2 times t. T because that's the argument, or the argument to f, right, in this integral. Okay, so then the integral of 0 over any interval is going to be 0. And so then what we're left with is this integral from 0 to x of 2 times t dt. Now again, we can pull the constant 2 outside of the integral using properties of integration. All right, so that's straightforward. And then again, we're going to use the fundamental theorem of calculus. All right, and we know that, let me go back to this slide here, we know that the antiderivative of the function t is t squared over 2. So by the fundamental theorem of calculus, all right, we get this expression here. So t squared over 2, we have to evaluate that at x, the upper endpoint of integration, and then 0, the lower endpoint of integration. All right, I've pulled the 1/2 out, so I have 2 times 1/2, which is going to be 1. So that I've combined a few steps there, but I'm sure you can follow along with that. And then finally, we get x squared minus 0 squared, or x squared. So we take these three results. This result here, all right, that says that f of x, cap f of x, the CDF, is equal to 0 for any values of x less than or equal to 0. We take this result here, that the CDF is equal to 1 for any value of x greater than or equal to 1. And then this result here that says that for values of x between 0 and 1, the expression for the CDF is given by x squared. So we take all those results together and we get this fully specified expression for the CDF. All right. Now a few things to note. Again, because of the way that we have expressed this CDF, you'll note here that we have included a place for every real number that is possible. All right, values of x that are less than or equal to 0, values of x that are greater than 0 and strictly less than 1, and values of x that are greater than or equal to 1. And so this CDF, this function that we've come up with, is defined at every real number. In addition, it's a non-decreasing function over the real line, which it necessarily needs to be. In addition, over the unit interval from 0 to 1, it's a strictly increasing function. All right. Note also that the CDF is equal to 0 at or to the left of 0, which is the lower boundary of the sample space. And then the CDF is equal to 1 at or to the right of 1, which is the upper boundary of the sample space. Now let's compute some probabilities. Now you'll remember that when we first started talking about the PDF, and the conditions that the PDF must satisfy, the third condition said that the PDF can be used to calculate probabilities involving x, the probability that x takes on a value in some interval. All right, and but we also know that we can use the CDF for that purpose as well, as long as the interval over which we want to compute the probability of x being within is of the appropriate type. And this is true for this particular probability that we're wanting to compute. So we want first the probability that x is less than or equal to 1/2. Well, now we recognize this as being the same exact kind of probability that is provided by the CDF. In particular, if I go back a few slides here, all right, in fact, let me back here. We see here when we define what a PDF or what a CDF is, we see that the CDF evaluated at a particular point is defined to be the probability that the random variable is less than or equal to that value. Well, this is exactly the kind of probability that we're wanting in this particular example, and so we can obtain this either by integrating the PDF, but also by evaluating the CDF at that particular upper point. And it really makes sense to do that in this case because we've already done the integration to get the CDF. All right, and so here we are. We're wanting the probability that x takes on a value less than or equal to 1/2. All right, and that is specifically provided by or given by the CDF evaluated at 1/2. Now 1/2 is between 0 and 1. Okay, and so we know that the expression for the CDF over four values of x in that interval is x squared. Okay, so we evaluate, we plug in 1/2 into that expression, so 1/2 squared and 1/4. Okay, so the probability that x takes on a value less than or equal to 1/2 is 1/4. Next, we want the probability that x takes on a value greater than 3/4. Now, we could obtain this by integrating the PDF from 3/4 up to positive infinity, and then going that route. But we can also rewrite this probability that we want using the complement rule as 1 minus the probability that x is less than or equal to 3/4. And that's helpful to do because this probability here is given to us by the CDF evaluated at this upper endpoint of 3/4. All right? And so the probability that x is greater than 3/4 is equal to 1 minus the CDF evaluated at 3/4. Now again, because 3/4 is between 0 and 1, the CDF evaluated at that point is equal to the square of the argument to the CDF. And so this is equal to 1 minus the square of 3/4, so 1 minus 9/16, and so we get 7/16. So the probability that x is strictly greater than 3/4 is 7/16. Now, to compute the probability that x is strictly greater than 1/2 and less than or equal to 3/4, I want to point out this next statement here. Note that the probability that x is less than or equal to 3/4 is equal to the probability of the union of two events. The first event being that x is less than or equal to 1/2, and then union with the event that x is strictly greater than 1/2 and also less than or equal to 3/4. So just take a look at that and just convince yourself that the union of those two events is equal to the event that x is less than or equal to 3/4. X is going to be less than or equal to 3/4 if and only if it's less than or equal to 1/2, or it's greater than 1/2 but less than or equal to 3/4. Now, the reason that this is helpful is because we have the union of disjoint events. You would agree that these two events, the event that x is less than or equal to 1/2 and the event that x is greater than 1/2 but less than or equal to 3/4, those are mutually exclusive events. They're disjoint. And so we have the probability of the union of two mutually exclusive or disjoint events. And so by axiom 3, we can decompose the probability of the union of these two events in terms of the sum of the probabilities of the individual events. Okay? Now, the reason that this is useful, what are we looking for here? We want the probability that x is strictly greater than 1/2 and less than or equal to 3/4. And that is right here. So we have an equation with the probability we want. All we have to do now is solve this equation for that probability, and we get that the probability that x is greater than 1/2 and less than or equal to 3/4 is equal to this guy, the probability that x is less than or equal to 3/4, minus this quantity, the probability that x is less than or equal to 1/2. Now, you might say, okay, why is that helpful? Well, it's helpful because each of these probabilities can be obtained from the CDF, right? This probability, the probability that x is less than or equal to 3/4, is given by the probability that, is given by the CDF evaluated at 3/4. And the probability that x is less than or equal to 1/2 is given by the CDF evaluated at 1/2. And since we already have we already have the CDF, and we've already calculated some of these probabilities. In fact, we already calculated the probability that x is less than or equal to 1/2. We found that to be 1/4. And we also evaluated this guy too. So that is 3/4 squared, or 9/16. So what we end up with is a really nice way to calculate the probability that x is greater than 1/2 and less than or equal to 3/4. It's given by 5/16. Now, that's not the only way that we could calculate this probability. In particular, we could obtain this probability of 5/16 by integrating the PDF, which is 2 times x, over the interval from 1/2 up to 3/4. And if we were to do that, we would get the same exact value, 5/16. But the benefit of using this approach, or the reason for using this approach in this particular situation, is because we already had the CDF. We already had CAPF, which gave us probabilities of interest. Okay. Now, what do these two functions look like? What do the PDF and the CDF look like? Well, I've produced in SAS the graphs of these two functions. So this is a plot of the PMF of x. So for values of x that are less than or equal to 0 or greater than or equal to 1, the PDF is equal to 0. Notice I call this, I've got this labeled the PMF. That's incorrect. It's the PDF. I need to go fix that in my SAS program. Okay, you should correct that in your notes. Replace that with PDF. All right, and then for values of x between 0 and 1, then the expression for the PDF is 2 times x. So this is a straight line, all right, with a slope of 2. And then the CDF looks like this. For values of x less than or equal to 0, the CDF is equal to 0. For values of x that are greater than or equal to 1, the CDF is equal to 1. And for values of x between 0 and 1, the expression for the CDF is x squared, the quadratic function. Now, this last example illustrated the use of a general result that often proves very useful, namely that for A strictly less than B, the probability that X is greater than greater than A and less than or equal to B is equal to the probability that X is less than or equal to B minus the probability that X is less than or equal to A. Now, this is useful because this is just the difference between the values taken on by the CDF at B and A. So let me point out something very important here. We need to look at the inequalities here and pay very careful attention to them. So again, what we have here is the probability that X is strictly greater than A and less than or equal to B. And that this is equal to this difference between the CDF values. The CDF evaluated at the upper endpoint minus the CDF evaluated at the lower endpoint. So the leftmost inequality here is strict, but the rightmost inequality is non-strict. It's less than or equal to. Now, this result is true for any distribution, regardless of whether it is the distribution of a discrete random variable or of a continuous random variable. So this this formulation will always be true. Now, note that when X is a continuous random variable, the probability that the random variable X is equal to a particular value, which I'll denote by lowercase x, is given by the integral of the PDF from x to x. Okay? Now, the antiderivative of the PDF is the CDF. And so by the fundamental theorem of calculus, this integral is equal to the CDF evaluated at the upper endpoint minus the CDF evaluated at the lower endpoint. Well, that is just 0. So in other words, the probability that the continuous random variable X takes on a particular value X is always 0, and this is going to be true for any value. So let me say that again. When we're dealing with continuous random variables, the probability that the continuous random variable takes on a particular value is always 0 for any specified value. Now, this may seem counterintuitive, but it follows from the nature of continuous random variables themselves. Whereas discrete random variables take on the particular values in their sample space with positive probability, continuous random variables take on values in intervals with positive probability. So this has important implications in probabilities such as the probability that X is less than or equal to B. In particular, note that when X is a continuous random variable, the probability that X is less than or equal to B is equal to the probability of the union of these two events. The first being the probability that X is equal to B, and the second being the probability that X is strictly less than B. And the reason is X is less than or equal to B if and only if it's either equal to B or it's less than B. Now, these two events that are connected with union or connected with the logical or, if you want to think of it that way, these are disjoint or mutually exclusive events. And so by axiom 3, the probability of their union is equal to the sum of their individual probabilities. Now, we've just shown that if X is a continuous random variable, then the probability that X is equal to a particular value B is just 0. And so it turns out that when we're dealing with a continuous random variable, the probability that X is less than or equal to a particular value B is equal to the probability that X is strictly less than B. In other words, in probabilities involving continuous random variables, we can change inequalities from strict to non-strict and vice versa without changing the value of the probability. So this implies that for real numbers A and B, where A is strictly less than B, the probability that X is greater than or equal to A and less than or equal to B is equal to the probability that X is strictly greater than A and less than or equal to B, which is equal to the probability that X is greater than or equal to A, but strictly less than B. And finally, this is all equal to the probability that X is strictly greater than A and strictly less than B. So in other words, when x is a continuous random variable, all of these probabilities are equal. Now let me just point out a word of caution here. Fiddling with inequalities like this cannot be done, absolutely cannot be done when working with discrete random variables. Because if either A or B happens to be a mass point, in other words, one of the values in the sample space of the random variable, then these kind of alterations will, in general, affect the probability. But when we're dealing with continuous random variables, all of these, each of these four probabilities are all equal. Now, before we wrap up, I want to go back and look at some of these calculations. All right. So we started off this example by finding C, and the way that we found C was that we integrated the PDF over the real line, and then we found the CDF, and that involves integrating the PDF as well. And what I want to show you are some different ways of finding these integrals, or integrals like these. For those of you who maybe are a little bit rusty on your calculus and may want some help, or maybe you want to check your work after you've done these calculations by hand. And so the way I'm going to show you a couple different ways, and these are perfectly fine, for doing these kinds of things on tests and assignments and things like that. This is not a calculus course, so the primary purpose is not for you to have to do things by hand. The purpose is for you to be able to use some calculus to find answers that are of interest in the context of a statistical theory class. And so because of that, I don't really care how you calculate the integrals. I just want you to be able to evaluate them. And so this first method involves the TI-83 or 84 calculator. I did this on simulation software for a TI-84, which I believe I've shown you in the past. And so on the TI-84, and like I said, this also applies if you happen to have an 83, but unless you've had the calculator for a long time, you probably don't have an 83. And if you were going to go buy a calculator like this, I would not recommend buying an 83. I would recommend buying an 84 or something like that. But anyway, if you press the math button on the TI-84, then this is what comes up. And you've got several menu options across the top. And what we're focusing on right now is the math menu. And if you look down here, option number 9, this is the function on the 84 calculator for doing integration. And in particular, it's going to be doing what's called numeric integration rather than symbolic integration. What we've been doing by hand is called analytical or symbolic integration. This particular calculator does not have the capability to do symbolic integration, but it will do numeric integration, which is a method of approximation. So it will give you the values. If we have definite integrals, it will give you the value of the integral or via approximation. So when you press when you select this option, either by scrolling down and selecting it or by pressing the number 9, then you'll get a wizard that you can then fill in, and it will calculate the integral. Now here is an example of what I'm talking about. So one of the calculations we had to do was to integrate x from 0 to 1. And let me go back here. This is where we had to do that right here. We had to integrate the function x from 0 to 1. And so when you select this integration menu option, you're going to get a wizard, that looks like this integral sign, and it'll have blank spaces for the lower and upper endpoints, and then for the function, and also for the variable of integration. And so what you need to do is you need to enter the lower and upper endpoints of the integration, and you also need to plug in the function, which in this case was just x. And then you will scroll over using the arrow key and enter X in that position as well. When you do that, then you're going to get 0.5 or 1/2, which is what we got before, okay, without the C. And so then what we need to do is we need to solve this equation for C. And so this is when we do that, that's how we got 2. So this shows you how you can do that kind of a calculation on the TI-84 calculator. Now, suppose we want, and let me go back to the notes here, suppose we want the probability that X is less than or equal to 1/2. Well, this is going to be given by the integral, as we saw. Let me see here. Scroll to it. Okay, this can be obtained by evaluating the integral from 0 up to 1/2. All right, and so that's what I've got right here. We have to integrate the PDF, which we now know is 2 times x. Okay, 4 values of x between 0 and 1. We need to integrate that function between 0 and 1/2. And when we do that, we get 0.25 or 1/4, which is exactly what we got doing it analytically. All right, if we want the, let's see here. All right, we could find, let's see here, the probability that x is between 1/2 and 3/4. Okay, 0.5 and 7/5. So we could find that very easily by integrating the PDF over that interval. We get 0.3125 or 5/16. Okay, now we also want the probability that x is strictly greater than 3/4. Now, because the sample space of x is the unit interval from 0 to 1, x is strictly greater than 3/4 if and only if it's greater than 3/4 but less than 1. All right, and so we can find that probability by integrating the PDF 2x from 3/4 up to 1, and we get 0.4375 or 7/16. All right, and then finally, we may, well, I think we've got more here, but if we wanted to verify that PDF does, that the PDF is equal to 2x over the unit interval, and that when we integrate the PDF from 0 to 1, we get 1, as it should be, then we can verify that using this calculation. Now we can also plot the PDF and the CDF on the TI-84 calculator, and so I've done that here. If you're familiar with how to graph functions on the 84, then you can see here that this is exactly the graph that for the PDF that I was able to construct using SAS graphing software, and that this is exactly the type of the look of the CDF that I got when graphing it using SAS software. So if you have the TI-84 calculator, you feel free to use the capabilities of that calculator to help you with the calculus. Now let me show you one more tool that you may or may not be familiar with, but my guess is that each one of you has a very nice tool that you can use to do some of these calculus calculations. All right, and what I'm talking about a smartphone. Now this is pretty neat actually, and I did this. This was on a on an iPhone using Siri. Now, if you've got another kind of phone, it may work as well. What Siri is doing is it's making use of Wolfram Institute and Mathematica and what's available online, their capabilities online. And so, for example, with Siri activated, I asked Siri, and this is exactly what I said. I said, Siri, integrate 2x from 0 to 1/2. And almost instantaneously, this is what came up. So I get a representation here. Let me see if I can blow this up a little bit so we can see it better. I get the integral that I want, integral of 2x dx from 0 to 1/2, and it gives me the value of 1/4, which is exactly correct. I also asked Siri to integrate 2x from 1/2 to 3/4. Okay, we just did that a second ago with the TI-84 calculator. And look at this. Not only does Siri give me the decimal representation, but even prior to that, Siri gives me the fraction representation. So what's interesting here is that Wolfram Alpha, they're actually doing symbolic integration. Okay, not just numerical integration. They're doing symbolic integration, which is available in Mathematica. And so you can ask Siri or your own smartphone if they may be able to do some calculus for you. Here's an example. I asked Siri to integrate 2x from 3/4 to 1. And we got 7/16 as the fractional representation. Again, Siri is doing, Wolfram Alpha is doing this symbolically and then giving us both the fractional representation and the decimal representation, or in some cases a decimal approximation. Here I'm asking Siri to integrate the PDF 2x from 0 to 1. All right, and so this is, I'm asking Siri to plot the graph of 2x from 0 to 1. That's right. And so I get this nice graph. And then it also gives me some additional information down here that I'm not really interested in this course. But that is very interesting. Here I'm asking Siri to plot the CDF, which is x squared from 0 to 1. So this is what I asked it to do, plot a graph of x squared from 0 to 1. And then by interfacing with Wolfram Alpha over the internet, okay, it came up with this plot. So, it's kind of neat, whether it's how useful it is. If we've got more complicated kinds of functions, then it may not work. But certainly the TI-84 calculator is able to do these things and provide the kind of approximations that would be useful for us, certainly adequate for what we're doing. And we can also integrate things by hand analytically, symbolically, right, to get these answers. But the bottom line is, that you've got quite a few tools that you can use to do the calculus, whether doing it analytically or doing it numerically with a calculator like the TI-84, or some of the Casio calculators will do it as well, and also the several HP calculators will do it. So I'm going to stop the video at this point. It's getting somewhat long, and it'll take longer to process, so I'm going to stop this now, and we'll pick up the next example in the next lecture video.